Hello students, welcome to the channel Statistica Hub. So this is our lecture number 14 in the course SH201A probability theory. In this particular lecture, we are going to cover something about the negative binomial distribution. The point is like we are not going to be like very deep into the negative binomial distribution, but some basic idea like what is the meaning of negative binomial distribution and some properties of the negative binomial distribution. So let's start with the lecture. So we are having the idea like how do we define the negative binomial distribution? So the idea just remain the same. See, every time I'm making use of the Bernoulli distribution. So in this one also, we are going to start with the Bernoulli distribution. So if you go for the geometric distribution first, in the geometric distribution, we were saying that number of trials required to get the first success. Correct? But in this particular part, there will be different thing. In spite of the first success, we are going to have certain number of success. The only difference. So if you go for the definition, then the definition says that in negative binomial distribution models, the number of trials required to achieve a specified number of success in a sequence of independent, identically distributed Bernoulli distribution. So that means to say you are having the x1, the first trial, that is a Bernoulli distribution with parameter p. We are having x2, the second Bernoulli trial with a parameter p. The p just remains same in all of them and they are independent of each other. So you can see I is independent of some xj. Okay, so that is the idea that you are having infinite number of Bernoulli trials or maybe some number of trials. And in this particular part, I'm just saying that we are having, in spite of first success, we are counting certain number of success. Okay, that means to say how many trials are required to get maybe R number of success or maybe K number of success. Anything. So let's say what is the probability formula? So probability x equal to k. That means to say you need k trials to get R number of success. Very simple. So the meaning of this particular thing is probability x equal to k. That means to say k trials are required. K trials are required to get R number of success. Okay. So let's try to see like what can be the answer. So in this particular part, the point is the trials required to get Rth number of success, yeah, or you can say R number of success. So that means to say the trials can't be less than R. To get R number of success, at least you play the game for R number of time. So in this particular setup, this K, the support of the random variable, the negative binomial random variable, that will be R plus 1 and so on. Like the minimum value that is possible for the K, that will be R only. Correct? Because you need to have like at least R number of success. Okay. So that is the number of success R, the P, the probability of success in each of the trial. Now we have to write the probability distribution. So the idea in this particular thing is like, let's say you are going for X equal to K number of trials. So 1, 2, 3, and so on. Let's say this is the Kth trial. And in the Kth trial, there will be success, correct? So you are left with K minus 1 number of trials. And at this particular place, this is the the Rth success, correct? So you are left with R minus 1 number of success in the previous zone. So if you try to write the probability function, probability x equal to some K, that will be, you need K minus 1 success out of R minus 1 trial. So R minus 1 C K minus 1, the probability of success that is P, that is R minus 1 times for these one, and there will be the final one. So that will be R. And we are having the failure. So the remaining points that are the failure. So Q raised to the power K minus R. So that is the probability formula. Okay. So I hope that makes sense, like how this is coming up. Very straightforward. We are having the setup. How do we define the negative binomial distribution? And we are getting the probability function just similar to the binomial distribution. Okay. So that was the first thing. Moving ahead in this part. So in this particular part, if you go for the mean value, the expectation of x, that will be coming out to be R over P. Okay. The variance, that will be R into Q over P square. And the probability function that we already covered. So the expectation of x, that is R over P. The variance of x, that is R Q over P square. Okay. Apart from this, you can go for the CDF also. So that will be probability that we are having the x less than equal to some x. So simply write that k is running from 0 to x and k plus R minus 1 CK. The other form that you can write, and simply Okay, there is one more formula for this particular part. If I say that X follow the negative binomial distribution, then in that, like the thing is like you can write this particular thing to be this thing also. So we are having like the negative binomial distribution probability X equal to K. Sometimes this formula is also used. K plus R minus 1 C K Q raised to the power K P raised to the power R. This is another formula. Sometimes it is also used. So you can use this one also. We are having this thing, then you can write 1 minus P raised to the power K and P raised to the power R. So that can be the CDF in this particular part. Okay. Moving ahead with this particular thing. So like in this particular part, don't go for the derivation, that will be like time consuming. So in case you want to follow the derivations, then you can follow any standard book. You'll be finding the proper derivation. But I suggest you to just remember what is the mean and what is the variance and what is the MJF that we are going to see like in a while. So we are having expectation of X. That will be simply this form. If you expand and if you just solve this thing, you'll be getting R over P. Okay. Moving ahead. Similarly, if you go for the variance, that will be coming out to be R into Q over P square. And if we move ahead, then if you go for the MGF, this is again an important part. So we are having the MGF that will be coming out to be P e raised to the power T over 1 minus Q e raised to the power T raised to the power R. So you can see one thing, this is something that we can observe, that is like for the, we have just covered the similar kind of thing for some other distribution, and we are just going for the R time, right? For the geometric distribution, you got the similar thing. You only got this particular part. In the geometric, you are saying that number of trials required to get the first success. In this particular part, we are going to go for number of trials required to get the R number of success. So due to that particular reasoning, this is coming out to be P e raised to the power T over 1 minus Q e raised to the power T raised to the power R. So remember this one. Okay, then if I move ahead, then we are having some examples like where we can observe the negative binomial distribution. So if you go for the number of coin flips until you are obtaining the three heads. So you're flipping of the coin again and you are sloping once you get the R, that is 3 in this case. So that is modeled using the negative binomial distribution. If you go for another example, let's say number of defective items found in a batch until finding the 5 defective items. So you're going to maybe quality control again and again, and you stop once you get the 5 defective items. So that is again something modeled using the negative binomial distribution. Then if you go for the third example, that is the number of success, 3 throws before missing 2 shots. Again, a negative binomial distribution. Okay, now this is one of the examples. So let's see the example. So if the probability of success in a single trial that is given to be P 0.2. Okay, what is the probability of requiring exactly 10 trials to achieve 3 success? So things are coming out to be very simple. You are saying that R that is coming out to be 3 and you need to get probability X equal to 10. That you need 10 trials to get 3 success. So that will be 9C3, the same formula, 0.2 raised to the power 3 because we are having 3 number of success and 0.8 raised to the power 7. So simply using the formula and using the definition, we are getting the probability for X equal to 10 in this particular example, that will be coming out to be 0.060. Okay, so this is a very simple example. And in fact, if I just say like what we have to cover for the negative binomial distribution is, always remember how we define the negative binomial distribution. So you have to memorize few things, or to understand the concept, you have to understand how do we define negative binomial distribution. That is very important, like how this is framed. Then you have to memorize the probability function. Then you have to memorize the expected value that is coming out to be R over P. Then you have to memorize the variance. So variance of X, that will be RQ over P square. And you have to go for the MGF also. So MXT, that will be P e raised to the power T over 1 minus Q e raised to the power T raised to the power R. So if you remember these things, then well and good. And one more thing, what are the possible values of X? So we already covered R, R plus 1, and so on. It will be going till infinity. Okay, so these are the things that you have to memorize, and always follow like the slides, then follow some standard book, go over some different examples. Okay, moving ahead. Okay, these are some of the examples, and again, like where you can use this one. So we can go for like modeling in the course of like the most example is the most I can say the most simple example. that we can observe that can be in the quality culture, right? A company may be rejecting something if they are going to find maybe 5 defective items in a particular lot. So you are going to try a lot of like you just go and you just observe different items from the same lot, and you stop once you get the 5 defective items. So that is the idea. So in these parts, we can make use of the negative binomial distribution. If you are in some epidemiology or something, so these are like a lot of examples. So any distribution, anything that you are going to encounter with, you can think about many examples and you can just use that like in any context. Okay, like one example that is already been given. So number of patients examined until you are finding the 5 with a specific disease. Okay, so that was something about the negative binomial distribution. So I hope you are able to understand what is the meaning of negative binomial distribution and what are the key features of a negative binomial distribution. So that was all about lecture number 14. Thank you. Bye.